Subject name is operating system. Unit number is 1. Title of the unit is operating system overview. Topics to be covered in the system is computer system overview, which consists basic elements, instruction execution, interrupts, memory hierarchy and cache memory. Basic elements of a computer system consist processor, main memory, I/O modules and system bus. Processor. Processor is referred to as CPU, that is central processing unit, which controls the operation of the computer and performs the data processing function. Processor consists of the following internal registers: memory address registers, which specifies the address for the next read or write. Memory buffer register contains data written into memory or receives data read from memory. I/O address registers and I/O buffer register. Main memory. Main memory is referred to as real memory or primary memory, which is volatile in nature. We will see what is volatile. Volatile is content of the memory is lost when the computer is shut down. Main memory is classified into two types: read-only memory and random access memory. I/O modules moves the data between computer and external environments such as secondary memory devices, communication equipment and terminals. System bus. It is a single computer bus that connects the major components of a computer system, combining the function of data bus to carry information and address bus to determine where it should be sent and control bus to determine its operation. Communication among processor, memory and I/O system taken place within the system bus. This diagram represents the top level view of computer component: CPU central processing unit, PC program counter, IR instruction register, memory address register, memory buffer register, I/O address register and I/O buffer registers. Instruction execution. A program consists of set of instructions stored in memory. Two steps: processor reads or fetch instruction from memory. Processor executes each instruction. First fetches an instruction from memory and stores that instruction in the instruction register. The instruction is then decoded and may cause operands to be fetched from memory and stored in some internal register. After the instruction on the operands has been executed, the result may be stored back in memory. Instruction cycle. Sequence of instruction is executed by the processor by going through instruction cycle. This diagram represents fetch execute cycle. Instruction fetch and execution. The processor fetches the instruction from memory. Program counter holds the address of the instruction to be fetched next. PC is incremented after each fetch. Instruction register. Fetched instruction is loaded into instruction register. The processor interprets the instruction and performs the required actions. Processor memory. Transfer data between processor and memory. Processor I/O. Data transfer to or from peripheral devices. Data processing. Arithmetic or logic operation on data. And control. Alter the sequence of execution. Interrupts. The occurrence of an event is usually signaled by an interrupt from either the hardware or software. Most I/O devices are slower than the processor. Processor must pause to wait for devices. Interrupts can be classified into two types: hardware interrupt and software interrupt. Hardware interrupt may trigger an interrupt at any time by sending a signal to the CPU, usually by the way of system bus. Software interrupt. Software may trigger an interrupt by executing a special operation called a system call. Interrupt service routine. When the CPU is interrupted, it stops what is doing and immediately transfer the execution to fixed location. The fixed location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes the interrupted computation. This diagram represents the interrupt service routine. Classes of interrupts. Program generated by some condition that occurs as the result of an instruction execution such as arithmetic overflow, division by zero, attempt to execute an illegal machine instruction, and references outside a user's allowed memory space. Timer generated by a timer within the processor. This allows the operating system to perform certain function on a regular basis. I/O generated by an I/O controller to signal normal completion of an operation or to signal a variety of error conditions. Hardware failure generated by a failure such as power failure or memory parity error. Interrupt vector. The interrupt must transfer control to the appropriate interrupt service routine. The method for handling this transfer to invoke a generic routine to examine the interrupt information. The routine is called interrupt specific handler. A table of pointers to interrupt routine is stored in low memory, that is first 100 locations. This location holds the address of the interrupt service routine for various devices is called interrupt vector. This array or interrupt vector of addresses is then indexed by a unique device number given with the interrupt request to provide the address of the interrupt service routine for the interrupting device. Instruction cycle with interrupts. After pitching, during execution process, it's going to check whether interrupt is enabled or disabled. If interrupt is disabled, it's complete a task. Otherwise, it initiate interrupt handler. After performing interrupted task, it's going to complete its execution stage. In this slide, we are going to discuss about the steps which is done by the operating system to complete an interrupt. Device controller or other system hardware issues an interrupt. Processor finishes the execution of the current instruction. Processor signals acknowledgement of interrupt. Processor pushes position status word and program counter onto control stack. Processor loads new PC value based on interrupt. Save remainder of the process state information. Process interrupt. Restore process state information. Restore all PSW and PC. Memory hierarchy. Major constraint in memory is amount, speed and expense. Memory must be able to keep up with the processor. Cost of memory must be reasonable in relationship to other components. Memory relationship can be defined as faster access time, greater cost per bit, greater capacity with smaller cost per bit, greater capacity, slower access speed. Memory relationship can be represented this way also. Faster access time, great cost per bit, greater capacity, smaller cost per bit, greater capacity, slower access time. But we can't achieve faster access time, smaller cost per bit, greater capacity. Memory hierarchy. The wide variety of storage system can be organized in a hierarchy according to speed and cost. The higher levels are expensive, but they are very fast. The lower level of the hierarchy, the cost per bit is decreases, whereas access time is increases. In this case, magnetic tape is very cheap, but its access time is very high. Register, the cost is very expensive, but its access time is very small. Main memory, RAM. The CPU can load instruction only from memory, so any programs to run must be stored there. General purpose computer run most of their program from rewritable memory called main memory. The main memory commonly is implemented in a semiconductor technology called dynamic random access memory, ROM. Computers use other forms of memory, read-only memory, and electrically erasable programmable read-only memory E2 PRAM. Because ROM can't be changed, only static programs such as bootstrap program are stored there. The immutability of ROM is of use in game cartridge. E2 PRAM can be changed but can't be changed frequently and so contains more static programs. Example, smartphones have E2 PRAM to store their factory installed program. Memory address. All forms of memory provide an array of bytes. Each byte has its own address. Load or store instruction. Instruction is achieved through a sequence of load or store instruction to specific memory addresses. The load instruction moves a byte or word from main memory to an internal register within a CPU. The store instruction moves the content of the register to main memory. Secondary storage. Main memory is usually too small to store all needed programs and data permanently. Main memory is a volatile storage device that loses its content when the power is turned off or otherwise lost. The main requirement for secondary storage is able to hold large quantities of data permanently. The most common secondary storage device is magnetic disk, which provides storage for both programs and data. Most programs are stored on disk until they are loaded into memory. Solid state disk and flash memory. Solid state disks are faster than magnetic disk and are non-volatile, which stores data in a large DRAM array during normal operation, but also contains a hidden magnetic hard disk and battery for backup power. If external power is interrupted, solid state disk controller copies the data from RAM to the magnetic disk. When external power is restored, the controller copies the data back into the RAM. Another form of solid state disk is flash memory, which is popular in camera and personal digital assistant in robotics, and increasingly for storage on general purpose computer. Flash memory is slower than the DRAM but needs no power to retain its content. The another form of non-volatile storage is NVRAM, which is DRAM with battery backup. This memory can be as fast as DRAM and is non-volatile. Cache memory. Store frequently used information and data for quicker processing by the CPU. Invisible to the OS, interact with other memory management hardware. Processor must access memory at least once per instruction cycle. Processor execution is limited by memory cycle time. Exploit the principle of locality with small, fast memory. Cache memory principle contains a copy of portion of main memory. Processor first checks cache. If not found, a block of memory is read into cache. Because of locality of reference, it is likely that many of the future memory references will be to other bytes in the block. This diagram represents the place of cache. Cache is placed between CPU and memory. The second diagram represents three-level cache organization. Cache read operation receives the address RA from CPU. Is the block containing RA in cache? If it is yes, fetch RA word and deliver to CPU. Otherwise, access main memory for block containing RA. Allocate cache slot for main memory block. Load main memory block into cache slot. Deliver RA word to CPU. Cache design. During cache design, we should consider the following factors. cache size, block size, mapping function, replacement algorithm, write policies, number of cache levels.